So, hello everyone, and welcome back to the Black Hole War series. Today we will present to you the third episode of this talk called A Curved Hope. I am Bilyana Tomova, a PhD student at University of Cambridge in theoretical physics, and here tonight to host this talk with me is Goncalo Regado, another PhD student in physics at Cambridge.
So, in our previous lectures, we discussed what black holes are and their peculiar properties. If you recall, black holes are objects in the universe with such a strong gravitational field that nothing can escape from them, not even light. In particular, all the information about an object is inaccessible once it falls in. However, as discussed in the previous two talks, Hawking showed that black holes do emit radiation and eventually evaporate. This begs the question, can we recover the information of what fell in from the evaporation process? Hawking said the answer to this question is no, but many believe that he is wrong.
To shed more light on this issue, tonight with us is Dionysios Anninos, a lecturer from King's College London. He graduated from Cornell University and obtained his PhD at Harvard. After that, he held research position at Stanford University, the Institute of Advanced Study, and the Delta ITP Fellow at the University of Amsterdam.
So Dionysios, thank you for joining us.
It's a pleasure to be here.
I see that you're joining us from space. Before we begin discussing whether information is conserved or lost, can you help us understand a bit what exactly information is and what it is not?
So first of all, thank you both for doing this and hosting this wonderful discussion. It's a pleasure to be here. I hope we have a good time discussing the wonders of black holes. And so let's start indeed with information. Information is a tricky thing, and it's rather abstract notion actually. To some degree, you could consider information to be a pattern or structure that has some ascribed meaning to it, that characterizes in some way or another a system. And in addition to this, information is something that has certain properties. In particular, information is a notion that can be transported, it's a notion that can be codified, and it's a notion that, most importantly, starting with early work on thermodynamics in the 19th century, and more recently with work of Shannon and von Neumann, is a notion that can be remarkably quantified. And so, as I said, it's a rather abstract notion, but we should think of it as some sort of ordered pattern or structure that meaningfully ascribes characteristics to a system.
So all this definition seems very abstract. Can you help us understand it better by giving us a more concrete example of an information?
Indeed, it is a very abstract notion, and I'm not sure how useful my definition was, but I think it's an extremely good idea to give some concrete examples. For instance, a system that contains information could be something as simple as the page of a book, where one has a set of words built from letters which convey a very particular meaning. A system that wouldn't contain information content, on the other hand, would be a system where you have a randomly selected collection of letters distributed in some disordered way. To give a slightly different notion of a system with information, we could imagine a collection of particles or bodies. This could be something as simple as billiard balls on a billiard table. And the information content in this system could be described as the location and speed and direction that every billiard ball has at a given moment in time.
Okay, so all these systems seem to be good analogies for information. But what exactly do physicists mean when they say that information can be lost?
Information being lost has to be dealt with in a delicate way. So I think the first thing we should take into account, and now we're speaking generally rather than in the context specifically of black holes, is that most systems that undergo some sort of interaction may seemingly lose information at face value. Just to specify what I mean by this, we could start with the following thought experiment, or in fact, an experiment we can do in our kitchen. Imagine you have a cup of coffee and you have a droplet of milk that you want to put inside the coffee. Initially, the droplet itself is something that has is a fairly well-specified physical system. It's located at some point. It has a certain amount of mass and position. But once it falls into the coffee, the particles in the droplet mix up rather efficiently with the remaining body of the coffee, and the original information content of the droplet, the height from which it fell into the coffee, for example, or its size or its initial shape, are very hard to reconstruct. There's a sense in which, at least to first approximation, the information of the original drop has been lost, since there could be many different droplets that lead to, at least seemingly, to the same mixture of coffee and milk. So there's a sense in which information in physical systems, particularly physical systems with a large number of constituents, built from a large number of constituents that are interacting with each other in some way, are very good at mixing up what may seem initially like a rather ordered or well-specified configuration.
So is this a simple matter of our ignorance, or is information in principle actually lost in these systems?
According to the laws of physics, although it may seem, if we are not careful enough in keeping track of the dynamical process of the evolution of our system, that is to say, at every moment in time, the location of every constituent of our system, it would seem that information is somehow lost. However, all known laws of nature that we know of at this stage, whether they are the macroscopic laws of nature or quantum laws of nature governing the microscopic world, indicate that that there is no process that can destroy information. That the best we can do is mix it up to an almost indistinguishable form from a random pattern, but that ultimately physical systems preserve in their evolution in time the original information content that we started with. And so as far as we know, physical systems rather robustly preserve information, but they're quite good at hiding it in subtle ways.
So thank you for this answer. This has been very interesting. However, the picture of information in terms of letters and coffees seems to be more clear now, but how do black holes, which are such an exotic objects, fit into this picture?
That's a great question. We have to think a little more broadly to fit into the picture, the story of black holes. As a way to connect to the previous examples, we could consider the following situation. We could imagine a large cloud of dust where the dust is comprised of little particles, each with their own position and speed and direction at some instant in time, so that we have an initial system whose information content is quite clear, a little bit analogous to the billiard balls we were discussing earlier on. And now we imagine that due to the force of gravity, this cloud of dust is starting to collapse into itself, eventually forming a black hole. So we could imagine such a system slowly collapsing, and once it forms a black hole, the original information content of the cloud of dust seems to be lost into the featurelessness of the black hole itself, which you may have seen in the previous discussions is a rather featureless object, specified only by the amount of energy it contains and the amount of speed that it has, or angular momentum. Now, although we specified the information content of the initial dust cloud collapsing into this black hole, and that was a very concrete information content, one could imagine many different dust clouds where the positions are slightly altered, or the velocities of the particles are slightly altered, that collapses into an essentially indistinguishable black hole. This is somewhat reminiscent then of the droplet of milk mixing with a coffee in such a way that the final state, which is the mixture of the droplet of milk and the coffee, it can stem from a large amount of possible initial configurations. Even at this simplistic level, we see that the information content of a dust cloud or whatever other celestial body may collapse into a black hole, it somehow becomes featureless, at least to some simple approximation that we're dealing with. Rather, at least to the approximation at which we're having this discussion. Yeah.
We said that in the case of the coffee, that even though seemingly the information for the milk droplets and its component is lost, if we are careful enough and use the equations that tell us how the particles of the milk evolve, we can actually recover all the information about their position and momenta. So can we just do the same thing for black holes then?
So that's an excellent question, and at the heart of the matter. You see, like I said before, and you correctly pointed out, for the example with the milk, indeed, it's a matter of us following the understood laws of nature at a careful enough level to show that information is in fact never lost in the system. The important distinction with the example of the black hole is that once the information of the original dust cloud or whatever other celestial body it may be collapses into the black hole and becomes featureless, we don't yet have a complete set of laws that informs us where this information may have gone. Regardless of the size of the computer that we may build in order to keep track of all the particles, at some point we don't know what the correct equations are to solve in order to show whether or not this information is preserved. This is lies at the heart of the puzzle of the information problem for black holes.
So that's very interesting. So we just discussed how, regardless of the configuration of the dust, then the black hole that is formed from collapse is featureless. We also learned from the previous talks that black holes evaporate. Naively, I would think that maybe in this evaporation procedure, we could recover some of the information. Would that be possible?
Great. So this question, which is another great question, lies at the heart of either sharpening the question of information for black holes as being lost or providing some hope for it to be recovered. And so we can discuss that a little bit now in the following sense. Once it was shown by Hawking that black holes, though featureless at face value, can indeed emit radiation of a thermal type once quantum effects are taken into consideration. We seem to end up with a few logical possibilities as to what happens to the evolution of a black hole. One might argue, as was originally done, that if the emitted radiation carries no information, which it seemed to be at the level of Hawking's calculation, which at the level of Hawking's calculation seemed to be the case, one ends up with a body that continuously loses its energy and shrinks in size until it becomes essentially non-existent. And all information of the original dust cloud is simply lost into the radiation, which according to Hawking's calculation, we might view as the random array of letters that we talked about earlier as an example of non-information, of a system with no information content. This would be an example, and perhaps the only example, in which the laws of nature lead to the loss of information. That information is so fragile in this case that it's lost, however carefully we may follow the equations that govern the system. The second scenario that we might imagine is the slightly altered version of this one, which was that although the radiation that Hawking calculated to be emitted by the black hole is indeed featureless, like the random array of letters that we discussed in our earlier example, that at some point, deep into the end point of the evaporation process, there remains a system whose physical properties are sufficiently altered that it no longer behaves in the simple way that Hawking predicted. The reason this might happen, or the reason why this scenario isn't precluded by Hawking's original argument, is that he needed to assume that the black hole was very large. And so if the final system is small enough in appropriate units, it could be argued that all of the information content of the dust cloud is encoded in this final system, which has been called a remnant in the literature. So this was a second scenario, that there exist these rather stable, long-lived objects carrying all of the information content in a remarkably efficient way of the original dust cloud, or whatever it may be, in the form of a microscopic microchip, so to say, containing all this information. And this was the suggestion of the remnant. The final logical possibility that people discussed and continue to discuss is the possibility that the information content is ever so slowly released in the evaporation process itself, but in such a subtle way that it is extremely hard to keep track of the original information with the current available mathematical tools we have. This was the proposal that was elucidated most clearly by Don Page in a fabulous paper that he wrote called Information in Black Hole Radiation. In this article, he made the case that although our current mathematical equations are not powerful enough to perform this calculation, it must be the case that information is slowly leaked out of the black hole throughout the evaporation process in the most delicate of ways. If you will, it's somewhat reminiscent, although in an imperfect way, to the idea that you start with an encyclopedia and you throw it into a fire and you let the fire burn the encyclopedia, and then you keep track of all of the dust particles and all the heat and all of the radiation being emitted in this process in order to reconstruct the original encyclopedia. The information content of the encyclopedia is emitted throughout the process. This is an imperfect analogy in the sense that the other foundational idea that Don Page proposed in his paper was the idea that crucial to the recovery of the information of the black hole is that we take into account quantum properties of this information.
So, wait a second. What are these quantum properties of information that you're talking about? How does information differ in the quantum world to the one that we're experiencing every day?
I'm very glad you asked. In fact, I got a little ahead of myself in mentioning the quantum properties of information. So let me backtrack and discuss and try to elaborate on the difference between these two systems. But before doing so, let me re-emphasize again that both for the quantum world as well as the macroscopic, or as physicists like to call it, classical world, information is indeed robust and preserved. We sometimes have a picture of the quantum world being a probabilistic world where things are fuzzy. Nonetheless, there's a very sharp sense in which information is just as robust and just as preserved in the quantum world, according to the quantum laws that we know of, as it is in the classical world. In addition to this, it's important to emphasize that both in the quantum world that governs the microscopic laws of physics, as well as the macroscopic world, information can be rather fragile. This is something that both systems have in common. Both worlds, sorry. This is something that both worlds have in common as well, the fragility of their information content. The important difference between the two types of information appears at a slightly different level and has to do with the fact that the classical world is a world in which we can keep track at all times of our system in its given realization. In the classical world, we keep track of the realization of the system in a completely deterministic form from beginning to end. To give a concrete example, imagine we had a billiard ball again on our billiard table. At any moment in time, in the classical world, the location of the billiard ball and its speed and direction are well specified notions. This concept has to be slightly altered in the quantum world because of what physicists call the notion of superposition. In the quantum world, systems can live not just in these deterministic configurations that we just discussed for the billiard balls, but rather they can live in superpositions of various possible evolutions at the same time. And all of these are equally real and equally concrete until one of them is measured by an external observer. And so this is the complicated concept that needs to be grasped in the quantum world. Now, the fact that this is the case, as has been confirmed by countless experiments, leads to a slightly different notion of the information content of the system. And this has become an active field of research over the last few decades, known as the quantum information question. Just to give you a flavor of the difference between quantum information and classical information, I think it's important to elaborate on one final concept. And I apologize for all of the concepts that we've introduced throughout this discussion, but I don't know quite how else to do it. In order to elucidate the difference between the kind of information that a classical system or a macroscopic system can encode as opposed to a quantum system, I'd just like to mention two simple examples. In the first example, we imagine that we have a system that carries some electric charge, say 2 units of electric charge, and that this system splits into 2 subsystems due to some process where we each carrying some fraction of the original electric charge. This fraction could be that one system carries 2 units of the original electric charge while the other carries none. It could be that they split equally into 1 unit of electric charge and another unit of electric charge. Or it could be some other configuration where one system carries a negative amount of charge and the other carries an even more positive amount of charge. There are various possibilities we could imagine. The important point is that if the original information of how much electric charge was contained in the system is known, once the system is split, the distribution of the original charge is contained, assuming the system splits into 2 systems, in the information content of one of the subsystems in a simple way. That is to say, if I measure that my subsystem has a single unit of electric charge, the other system must also have a single unit of electric charge so that the total charge adds up to 2, which was the information content of our original system. Whether we measure this or not in the classical world, this is simply the case at all instances in time after the system splits into 2 subsystems. In the quantum world, something rather different can happen. This has to do with, again, this notion of superposition. So we could have an analog of the setup that we previously discussed, except that until we measure the analog of the electric charge of the subsystem, it could in fact take a distribution of values governed by some probability. And so it's not deterministic from the get-go. It's only upon measurement that the system collapses, to use the word that physicists use, into a particular value, and in doing so fixes the value of the other system, however far it may be. This notion and distinction between the classical distribution of information and the quantum distribution of information content is something that physicists often call entanglement. Quantum systems can be entangled, so to speak, in ways and patterns that classical systems simply cannot. And due to this entanglement, the information content of a quantum system can be rather rich and rather elaborate. The proposal of Page that makes his paper even more remarkable is that he viewed in his paper the radiation and the black hole as 2 subsystems of an original quantum system. And he proposed, using various remarkable thought experiments, that in order to keep track of the information content of the original quantum system, we should really view the radiation emitted and the remaining black hole as 2 subsystems entangled in the sense that I described before of the original quantum system itself. In doing so, Page brought into the discussion of black holes some of the most fascinating notions of the subject of quantum information.
Wow, that was a lot of fascinating concepts to understand in one go. What do you think would be the key message or the key story that you'd like the audience to take in with them?
I think there's a few, and it really is a lot to take in for all of us. I think there's a few messages that are useful to keep in mind. One is that information is at the same time a very robust notion, a very robust quantity according to the currently understood laws of nature. But at the same time, it's rather fragile at face value if we're not careful about what properties of the system we keep track of. And so there's an interesting sort of 2-sided nature to information, which is robustness and fragility. And I think this is something important. The second message that's more specific to black holes is that in order to understand them, it seems that we have to take into account quantum properties. And this connects in a fascinating way what we typically ascribe to be the laws governing macroscopic physics. A black hole could be an enormous object, millions of times the mass of the sun. And objects we typically ascribe to the microscopic world, which are quantum features. We seem to have been forced, just through the reasoning of the problem, into a situation where we have to combine notions of the macroscopic world and properties of space and time with notions of the microscopic world and properties of the quanta. This is a remarkable opportunity and very much an open problem that we have to understand in a far more refined way as we continue to research, as we study. that we must understand in a far more refined way as we move forward. And black holes have provided us a wonderful avenue to do so.
Maybe a young member of the audience will one day solve this question.
Oh, I'm sure that'll be the case.
Thank you for joining us. For everyone who is currently listening to us, if you're curious how all these concepts come together to potentially solve one of the biggest mysteries in theoretical physics of the last centuries, join us again tomorrow at the same time. And good night.